This lesson deals with a common-emitter amplifier. You can find these notes in the ECE302 ebook in Chapter 5, starting on page 4. Let's do an example of what's called a common-emitter amplifier. And here I've got a transistor that's going to be biased in the active region. And what I've got hooked up here is an AC source that has a Thevenin equivalent. Typically this is a pure AC source, but if there's a DC component, we're going to block it with a capacitor. Let's assume that the value of beta F for this transistor is 100, and VBE on is around 0.7. A to F is 1, and this signal is just 1 millivolt sine omega t. We call the capacitors C1 and C2 coupling capacitors. They actually couple the input to the amplifier, and then couple the amplifier to a load. And then this is called a bypass capacitor, and we'll see why in a little bit in the notes. In Chapter 2, we talked about a 4-step procedure for analyzing an AC circuit with a DC biasing. Let's go back and use that again. Step 1 was to find the DC operating point. What we're going to do is replace every component by its DC model. The average voltage here would be the DC equivalent. That would be a short circuit because the average voltage would be 0 if it's a pure sine wave. A capacitor looks like an open circuit for DC in steady state. Likewise over here, and likewise over here. The battery that's here is a DC battery, so we'll just leave that there. For the transistor, we'll put in a DC model. Between the base and the emitter, there was a battery of VBE on, in this case 0.7, and a current source from collector to the emitter of beta FIB. This is our DC equivalent circuit for that amplifier. And you can see this looks very similar to something we did in Chapter 3 on pages 33 to 34, where we found I sub B, I sub C, and VCE. We found that IB was greater than or equal to 0, and the collector emitter voltage was greater than or equal to VCE sat. I didn't list the VCE sat for this problem, but we can assume it's around 0.2 volts. So our assumption checks. So we've done the first step of 4 steps. Step 2 in our procedure we developed in Chapter 2 was to calculate the AC model given the DC operating point results. For our model, there are 2 things, R pi and beta F. Beta F for DC and AC will be about the same. In this case, it's 100. We'll take a look at a little different idea a little later in the course. Our pi was A to F V sub t over I sub B at the operating point. A to F's around 1 for silicon. V sub t is around 26 millivolts at room temperature, and a value of I sub B on the previous page was 41.2 microamps. It gives me 631 ohms. Step 3 in our procedure is to put an AC model in for each component. I'm going to do this under a set of conditions which are called mid-band. In this particular circuit, we have 3 capacitors, and I did some rough calculations at different frequencies. We have a 47 microfarad capacitor, a 22 microfarad, and a 2200 microfarad capacitor. At 20 hertz, this looks like about 170 ohms in magnitude, and that's the magnitude of 1 over j omega c. As the frequency goes up towards 20 kilohertz, it begins to decrease. It's 0.17 at 20 kilohertz. Not as big a capacitor, so a little bit bigger value here, but again, a very small number as frequency goes up. And lastly, this very large capacitor looks like 3.62 ohms in magnitude at 20 hertz, very, very small value at 20 kilohertz. What this is saying is that if the frequency is high enough, the impedance of the capacitor is roughly a short circuit. We're going to use that as an approximation. In my circuit, I had 3 capacitors, C1, C2, and C sub E. I'm going to replace those by short circuits. And we'll see later with a simulation that indeed that's what happens, that the impedance of this capacitor is much smaller than what's in series with it or what's in parallel with it at the frequencies we're interested in, which are the audio band of frequencies from 20 hertz to 20 kilohertz. And we also have a battery in our circuit, and we talked about this in Chapter 2, that the AC resistance of a battery is the change in voltage over the change in current. But a battery has no change in voltage if it's ideal. And so there's a 0 value here, and then we're going to see there is a change in current. We'll take a look at it in a simulation in our next video. Here's my original schematic. I'm simply shorting the capacitors, shorting the power supply, and I'm applying my AC signal. And now I'm going to replace the transistor by its AC model. Between the base and emitter, I have a resistor of R pi whose value was 631 ohms. And between the collector and the emitter, I have a beta FIB, where we're talking about the AC value of base current. Little I sub little b, and multiplying that by beta F. A lot of ground symbols around here, so let's just redraw this. Something a little bit simpler to work with. Draw a common ground, and then between this node and ground, I've got V sub S. Between this node and the base, I've got 500 ohms, and then between the base and the ground, I've got 5K. Between the base and the ground again up here, I've got 10K. between the base and the emitter, but the emitter is grounded, I've got a value of R pi. My current source is between this collector node and ground, and then I have a resistor back to ground of 2K and a resistor back to ground of 1K. This is called a common-emitter amplifier because what's common between the input and the output for AC signals is the emitter lead of the transistor. It's been shorted out by this capacitor. Shorting this capacitor bypasses the signal from R sub E. That's why we call this a bypass capacitor. There are 5 things that we calculate for amplifiers that let us think about how we can use them and how we can compare them to each other. I'll also relate this to an equivalent circuit model in the supplemental problem sets. Let's take a look at calculating the following 5 parameters. First thing we're going to calculate on page 6 is a thing called the voltage gain, and that's the output voltage divided by the input voltage here. What's the output voltage? Well, the output voltage is going to be this current flowing into this load. So that's going to be a minus 100 I sub B times the parallel combination of 1K and 2K. The results are on the next page. I'll take a look at that just shortly. What's the value of I sub B? I sub B is going to be equal to the current in this resistor. And the current in this resistor is going to be the voltage across it, which is Vn, divided by 631. Here's our output in terms of the controlled source and the parallel combination. And then here's our value of I sub B, and we can substitute that in over here. Multiplying this out, I get a minus 66.7 thousand, and then the value of I sub B is Vn over 631. That gives me a value of a minus 105.7. And the voltage gain is defined as the ratio of the output to the input voltage, as shown on the previous page. That's a minus 105.7. What does a minus sign mean? Well, we're going to see an inversion. We have an AC input coming in for Vn, and it has a phase angle. We're going to see that the output phase angle is shifted by 180 degrees. And we'll take a look at this with a SPICE simulation in the next video. Another parameter of amplifier is a thing called the input impedance. Let's go back here. And it's the ratio of Vn to In. What this does is it forms a voltage divider with this resistor. But we don't want to voltage divide down our signal before we amplify it. We want to pick the input resistance to be much higher than this resistance. I purposely picked this to be 500 ohms to show you the effect of what we call loading. What is the ratio of Vn to In? Well, there's just 3 resistors in parallel here, so it's a parallel combination of 10K, 5K, and 631. That's 531 ohms. We're seeing a voltage division here of about a half before we amplify it. Kind of defeats the purpose of an amplifier. So when we're picking amplifiers, we're going to try to pick an amplifier that has an input resistance much higher than the source resistance or the Thevenin resistance of our input signal. And the results are on the next page. I'll scroll it at you shortly. Another parameter that we'll calculate is the current gain. It's the ratio of I out to In. I out is V out divided by 2K, or R sub L, and In is going to be equal to Vn divided by our input impedance, I'll call Zn. We'll look at this on the next page. We found Zn as the parallel combination of those 3 resistors, and now we're calculating I out and In, and then by taking their ratio, what's common is Vn. That drops out. And we get that the current gain depends on the voltage gain times the ratio of Zn to R sub L. You get a value of minus 28.1. The thing that we'll calculate for amplifiers is a thing called power gain. That's the product of the voltage gain times the current gain. Here it's almost 3,000. This is a little bit misleading. You really don't have any power gain at all. We're getting the power from someplace. We'll calculate efficiencies a little bit later in the course. But we'll see that when we refer to this, we're talking about the AC signals. This is the AC output divided by the AC input for voltage and likewise for current. But it's getting its power from the batteries in the circuit. The last thing we're going to calculate is a thing called the output impedance. This is defined looking back in the amplifier. It's really the Thevenin equivalent resistance. As we showed in ECE301 and 202, to find the Thevenin equivalent circuit, you remove the load, that was R sub L here, set all independent sources equal to 0, that's what was over here, and then find the resistance looking back in. This is a dependent source, and so we're going to leave it there. Looking back in here, we have a resistor, but we also have this controlled source, and this is not a resistor, but is a relationship. So we need to apply a test voltage, measure a test current, or vice versa would also work. If I apply a voltage V test, the current I test is going to flow, and then the current in this resistor is going to be V test divided by 1K, and the current in this controlled source is 100 I sub B. I have I test in terms of V test, but also in terms of I sub B. So I need another equation in terms of I sub B in either of these two. Let's sum the currents leaving this node. That would be this current here, this current, and then this current. The voltage, say it's Vn across these elements, it's also across here. So the current leaving the node would be Vn divided by 500. Vin divided by 10K, Vin divided by 5K, and Vin divided by 631. There is no current entering the node, so this has to sum to 0. The only number that works is if Vin is equal to 0. And that implies that I sub B is equal to 0. And that makes sense. There's no connection back this way. We therefore have I test is equal to V test divided by 1K plus 0. Our output impedance, called Z out, is equal to V test divided by I test, and that's equal to 1K ohm. When we design an amplifier, we want to make the output impedance as small as possible because it forms a voltage divider with the load. We want to make sure that we don't attenuate the signal once we come out of the amplifier. And lastly is our assumption about small signal valid. We were applying a 1 millivolt sine wave. We have to test the base emitter voltage. Let's go back to page 5 on the bottom. And the base emitter voltage is also Vin. The voltage here is going to be a voltage divider with R sub S and V sub S. Voltage here will be this resistance, which we actually called Zin, divided by 500 plus that times V sub S. Let's go back to page 7. And that's this expression here. V sub S was a 1 millivolt sine wave. We found that Zin was 531 ohms. This turns out to be 515 microvolts times the sine of omega t. Was that less than or equal to 8F V sub t? The sign goes between plus and minus 1, but the biggest it'll ever be is 1. And this is just a constant, 1 times 26 millivolts. 26 millivolts is greater than 515 microvolts. Our assumption of small signal was valid. If that's true, we can then add up the AC and the DC results. What we're doing here is we're throwing away terms in the Taylor series expansion that have squares and cubes in them. Let's solve for V out. Well, we did block the DC, so there's no DC in the output. And then our output is the voltage gain times Vin, but Vin is VBE. And we just found VBE as 515 micro times the sine of omega t. We found the gain to be minus 105.7. And that gives me a minus 54.4 milli times the sine of omega t. What this is saying is that we apply an input voltage of 1 millivolt, and the output voltage is in magnitude 54 millivolts, but there is a sign change, so there's a phase inversion in the output. Let me also solve for the voltage across the collector emitter. That's going to again be the DC plus the AC. And in our circuit on page 5, the collector emitter voltage was V out. We found in our biasing that collector emitter voltage at the Q point was 6.72. The output was equal to this. What we got is a DC level with an AC writing on top of it. We put a capacitor in to block that because we don't want to send the DC through an audio circuit to a speaker because the speaker would just simply move in one direction because of the DC voltage. This is the analysis of a common emitter amplifier.